Hello community! Today the most beautiful and the easiest way to build new agent to integrate new tools, and it is just gorgeous. And even when we looked here at Google and Stanford AI co-scientist, you remember we had 6 specialized agents and then we had 1 supervisor agent. And now imagine I told you, hey, if we have to add other agents, we have then a real problem because we have to retrain the supervisor agent and understand and all the other agents must know there's another agent we can communicate in a particular way we can communicate. And my goodness, this was really difficult. And now if we open up today, we want to have a training-free way, a user-friendly way, and an easily extensible multi-agent framework so we can tackle, I like it, complex scientific reasoning tasks across diverse domains, physics, mathematics, biology, whatever there is. So let's do this. So we will now create here new agents that can leverage here external tools. And tools is whatever you want a tool to be. I just created 3 different tools within the last 2 hours, and I want to show you how easy it is to do this with this new framework here by Stanford University. So whatever your tool is, a computer simulation, normal numerical simulation, multi-step thinking, if you have a particular Prolog compiler, whatever you want, just put it in there, build a tool, attach it to an agent, and in a multi-agent system, you will find a perfect solution. So with the new option to build here new tools for our specific use case, we simply add those to a multi-agent system without any training of the system. And this is such a nice step forward. So what is here the spark of genius, you might ask? Well, the concept of tool cards. It's simply a wrapper, a standardized wrapper that encapsulates here different tools, Python calculators, web search APIs, domain-specific modules, whatever it is. I mean, isn't this simple and beautiful? I'm amazed. So in this tool card, let's have a look, and I will show you multiple tool cards so you can build your own tool card. We have the tool itself, beautiful, and the tool metadata. Now the tool metadata, of course, the most interesting part, but let's start with the tool card. So we have a standardized format. This is important so that everybody knows exactly what to expect. Incredibly easy to add, replace, and expand here the tool set. We can work with 10, 20, 50 different tools. We just have to have some standardization. So we create a new tool card, not re-engineer the entire agent or the multi-agent system. And this is such a significant leap here toward a more advanced modularity. The tool cards need here clear metadata to make it easy for all the others to understand what the tools are available, how to use them, what are the limitations. So I would say, let's have a look now at the tool metadata. There are more or less 4 categories. First one is the tool functionality. I show you one, never mind, just to give you here an idea what the tool does. So this tool generates captions for images or whatever your tool is. Then, of course, you have to specify here the input-output format that are expected here. Then here, best practices, or maybe something could you see this is a constraint, this is not working really great. Please write it down. This helps the LLM so much to make your decision. And then some demo commands, some illustrative examples of how to use the tool. This really helps the performance here, I can tell you. So let's come here to the core idea of today. So we will have a lightweight algorithm for automatically optimizing the toolset for a specific task. So we do not start, like I showed you here, with Google from 7 or 8 agents that are fixed for a specific task, like to be a co-scientist. No, we have a task and the system will automatically choose from a given toolset, 20, 50, whatever, 2, 3 tools that are perfect for the job at hand. For my particular job, it will automatically optimize here the toolset. The problem we address is that if we run with the complete toolset that is theoretically available, if we enable all the tools, we have a noise from, 20 different LLMs. It will slow down the performance, and yeah, every LLM is hallucinating, so you can imagine. So we just want the minimum number for the perfect performance. Idea is simple. For an advanced context management, separate here the strategic reasoning from the actual execution of the tool commands. This is what they found doing here their experiments. So what we have, in essence, we have 2 modules. We have one module for the planning, the strategic reasoning, the planning, and then we have one module that executes here, for example, a Python tool environment. You see, easy. Now, the planner, just to give you an idea, inspects here the toolbox and loads now and looks at the tool cards. So it instructs now a set of n available tools, each with the metadata that describe the input, output, and the user's constraint. And rather than enabling everything, we have here a first guess what could be the optimal set of tools. Now, the planner module has 3 main steps you do have to understand if you want to write here a tool card. If not, I show you can play around, it's predefined, then just go and play. But if you want to write your own little module, these are the simple steps. Now, initialization of the planner, clear. Inspects the toolbox, loads each tool card, constructs a set of n available tools, each with the metadata that describe input-output schema, and then a subset might be selected based on whatever. Then we have the query analysis. So given now my personal, very specific query, mathematics, physics, whatever, the planner now formulates here a first level, high level tentative plan for the tool usage based on its initialization. The high level plan summarizes here the query objective, analyzes the required 6 skills that the LLM thinks that we need here, identify the relevant tools, and includes additional consideration to highlight the need for verification. I build a tool that says, hey, I don't have enough tool, please. I would need a tool that could do A, B, C. So I can build a meta tool to tell me as a human, hey, the system is missing here a specific tool for your specific task. So you can have so much fun here. So the high-level task plan provides you the global perspective of the final objective, ensuring that each subsequent sub-goal remains aligned with the original query. Isn't this great? Of course, we have a low-level plan that goes here for the sub-step, for the sub-goal in real-time, adapting new information at each single step. And then we need just a verification, no? And if we have a verification that says, check, green, go, we have here a summarization that brings us the solution. So we have a context verifier. I thought it's a module, but no, I just noticed that it's not a model reading here the literature. So just a context verifier checks whether a problem can be solved given here the current context. It verifies here 4 different elements. I will show you this in an example, like completeness. And once the verifier concludes that the query has been solved, indeed, a separate solution summarizer compiles here the final answer from all the trajectories. The executor model is relatively simple. Yeah? We have here the command prediction. So we introduce now a command generator that interprets here the planner's text-based action and produces here some executable, for example, Python code. So given the action at predicted by the planner, the command generator, of course it's an LLM, creates here a low-level command in the form of some executable Python scripts, calls the tool with the necessary input, and performs any required data preparation. Separating here the decision-making from the code generation increases here the performance, and then we have the command execution. So we do have a command executor, if you want, that runs here the generated command in a particular Python environment or whatever you like, obtaining now a result. So we have the tool output, the logs, the error messages, everything is available. And the executor then adds the current context to the step, trajectory, preserves the clear history of everything we have done. We have the result. Great. You know this. This is the study here by Stanford University. So nice. I really like this. It is already a week old, February 16, 2025. OctoTools, an agentic framework with extensible tools for complex reasoning. Yeah, this is exactly what we need in science. Have a look at this. So nice. We have everything. We have the code, we have the demo, we have the tool cards, we have visualizations, we have a beautiful paper. Everything is there. You can immediately start to build your own multi-AI agent system with the tools that you need. You build yourself your own tools, your tool cards, and you can integrate it in a multi-agent system. Couldn't be more beautiful. But you might ask, hey, is the performance there? Now, this is the data by Stanford. They compare it with Microsoft AutoGen or with LangChain performance, and you see this are the others, and with OctoTools you achieve this performance. What I found even more interesting is here the tool use in detail. They have 16 benchmarks. You find them in the published study. Look, this is here the OctoTool here from Stanford, and you see color-coded here. You don't only have in blue the general solution something, no? But you have a lot of different colors from image captioning, patch zoomer, text detector, Wikipedia knowledge searcher, Google search, text extractor, Python code, whatever. So you see, they are really all the tool at work. If we follow here the publication by Stanford University and they looked at AutoGen, you see AutoGen, 90%, they just use here the generalist. So this is almost like, hey, I just only use one LLM or VLM, and the rest of the tools hardly at all at work here to solve my problem. And GPT, function calling, or LangChain, Stanford tells us, hey, this is the same. So what I like here is this convinced me here. The better tools that you can design for your particular task, the better your performance will be. If you want to have a look here in detail here at OctoTools here for those 16 different benchmarks here, you see the blue is the generalist. And yeah, there is a generalist partition, but you see, the more complex it gets, the less general and the more the tool come into play. And this is just the standard tool set that they implemented, and this is free for you. Here you have everything compared here, numerical data performance here, OctoTool here, their performance, and here you have all the different data sets, modality, vision, general text, mathematical, scientific, whatever you get it. The Gaia text is real nice here, and they tell you, hey, this is our performance compared to a zero shot chain of thought to a pure base version where we have our standard tool base and non-optimize here the tools, or if you go here for the tool optimization, we achieve this result. So nice. You see, if you optimize your tool set, you get a much better result. If you want to see this in detail numerical data compared to AutoGen or LangChain, this is for you. If you want to see here an example, I think this is such a nice one. So we have here the query analyzer. You remember we have a summary, the required scale, the tools that are available here, additional consideration. And then in the first step, this here is the first step, we have the action predictor, the command generator, the executor, and then comes the context verifier, as I told you. It's not an own module here, as I understand it, but I told you there are 4 elements. Now, those 4 elements are completeness, inconsistencies, verification, and ambiguities. And if any of those gives a red flag, the conclusion is no. We have to do this again. We have to loop and run again. If somewhere, sometimes you get it that this says yes, green check mark, then we came to the conclusion and we can finish. So it's a relative simple idea, but beautifully executed. Now the real, I would say, intelligent here is here the tool set optimization. I mean, you can build it with the tool cards so fast. You can integrate your numerical code, computer simulation, high energy physics simulation, or astrophysics simulation, whatever you have. You just write here the tool card, you define input-output parameter, what a system can do, what other agents can use here this particular tool, and it is integrated in our multi-AI agent system. Task-specific tool set optimization. So we start here with a minimum set here of tools covering different modalities, language and vision. And if you have a robotic, you simply add robotics. And what's so nice is, you remember the Google Stanford co-scientist multi-agent system with 8 agents. It was rather specific for doing science in biomedicine. But what if you want to have a real general model? You don't care if it's biomedicine or physics or mathematics or engineering or material science or maybe even something in finance, You want to be open to the generality of your task. So this is here a powerful solution. It's really nice if you know your task and you say, hey, I can give you a best of example how I think that you should use my new tool that I now integrate here in the multi-AI agent system, and I give you a small set of validation examples. I found this out to be really helpful, but hey, try it out yourself. They have a simple automated algorithm to optimize the toolset configuration for each task. What they want, they have a higher complexity, and they want to break down the complexity to OFN. And they achieve this. And here you have the pseudocode, but if you want, I just write it down here for my green grasshoppers. This is easy. A baseline performance, and then we just exchange here the candidate. We evaluate this with every candidate change, and finally we aggregate the tools that yield here a positive improvement and combine them to the default set for the optimized toolset. Is this the most perfect optimization methodology? No. Does it work? Yes. So we go with them. So let's play nicing. This is so nice. Please have a look at the annex. At page 14 of this study, you see here all the different tool cards they give you. They give you the configuration here of the query analyzer, the action predictor, command, context verifier, solution summarizer. You have the complete prompt, complete code. If you want to have here, look here, you have the general solution, Google search, image captioner, PubMed search tool, Python code generator, text detector tool, oral text generator, Wikipedia. You have here the detailed information so you can easily build here a new tool card, a new tool for your particular task. I have here the Wikipedia knowledge search tool. So you have here, as I told you, we have to have a certain metadata, the tool name, the tool description, the input type that you expect, the output type that you expect, and the demo commands that you think are necessary. Plus, you give it here a simple example. That's it. That's the way you can build tools. So you can say, hey, thank you, Stanford Artificial Intelligence. Real nice. I will show you the license in a second. They have here an additional page where you have everything. The paper, the archive code, the GitHub code, the demo. Yeah, I want to show you the demo. Visualization. Yes, I have to show you visualization. You can have Twitter, yes, and Discord, whatever you want. It is there. So real nice documentation. This is exactly what we went through. The query analyzer, the task-specific toolset optimization, and the action prediction with the action defined here with a command generator, then the command executed, let's say in a Python environment. We get a context back. We verify that this is indeed the solution. We summarize all the solutions from all the different agents, from all the different tools. We have a final answer and we return it to the user. Visualization example. A lot of people ask me, hey, can we improve a visualization? Yeah, of course. If you go from an LLM to a VLM to a vision language model, we can run all of this example. Go there, just click at something. Just show you here the simplest example. We have a query. So we have a question. You are given a 3x3 grid in which each cell can contain either no kiwi, a fresh kiwi, and a rotten kiwi. Every minute, any fresh kiwi that is a 4-directional adjacent to a rotten kiwi also becomes rotten. What is the minimum number of minutes that must elapse until no fresh cell has a fresh kiwi? Solve this. So we know we have 4 minutes, but they just went with GPT-4 and say, okay, 19 baseballs. So there's something, so GPT-4 understood that this is a baseball, and then, yeah, there was something completely gone. And then you have here the prediction from the OctoTools framework. Yeah, if you scroll down, you have the complete reasoning. So you see, this is available for you. Have a look. You have here the visualization example from visual reasoning, multi-step reasoning, agentic reasoning, scientific reasoning, medical reasoning, a pathology diagnosis, and whatever. And here we have it now. You go to Hugging Face Spaces, and it's working for you. So you see, I've chosen here the GPT-4, the latest here for Omni-model. I defined my maximum steps as 8 out of 10, the maximum time, 240 seconds, yes. And then I just activated every tool that is available. So you just click the tool that you think as a standard set that is the tool for you. I went with everything I wanted to see if it really can perform this. I upload here an image. This is here an image from one of my videos. And then I ask a simple question. Hey, can you extract a logical path of reasoning from this image? And it has not the video, it's just this horror scenario. And then you just say, go, submit and run. Are you interested in the result? Okay. So it really came back and had some ideas what I'm depicting here. And it's not an easy task. And yeah, that's it. So query solved, beautiful. Try it out yourself. Have a look at all the different agents that are predefined, available for you, free of charge. It's so nice. I told you it's a GitHub repo available for you. There you have it. Just be careful because I told you we have to talk about the license. There is an MIT license, but there's also a CC BY 4. And remember, for BY 4, this is an open source license, but we have to give credit to the authors. So whenever you use this or you optimize this, you still have, and you want to issue a new license, you have to stick with this license and you have to give credit to the authors. Please remember this. Don't forget to do this. So here we are, closing remarks. We can integrate this new research now. Do you remember here my video where I showed you that we have 9 DeepSeek agents to augment a knowledge graph? And those were our 8 operational agents, where we had a relational extraction agent, a schema alignment agent, a conflict resolution agent, a pure evaluator agents. And now we can further give more tools to those agents. And you remember, an agent can be a tool to another agent. So it doesn't have to be that an agent only operates with multiple tools, but you can have an agent as a tool to another agent. This is then an intelligent tool, as we call it. Or think about this one, where we're talking about knowledge graph here with AI agents, where we have a particular form, a crystal form, where we have more or less a knowledge crystal that has some predefined structure from complexity theory, category theory. And I told you, we have here a little AI agent that now integrates here new knowledge interacting with the environment into our knowledge graph that has now an inherent crystal structure. Crystal, of course, here the pendant for a knowledge structure based on mathematical category theory and complexity theory. Now imagine this AI agent would have some specific tools to make it even easier or be able to compute here a higher complexity class of problems, extract this from the environment and build it into the new knowledge crystal. There are so many new ideas if we combine these technologies, just to give you an idea. And I told you, given the license, we have to give credit to the authors. So OctoTools here by Stanford University. Such a nice one. This is the team. Here you see the authors. Hey, congratulations. Just had a very first look, some hours, but it's really nice. It's really simple. You can integrate this. This is so nice. So don't forget to give credit here to the authors and you can play around. You can use this. You can apply this to your specific problem. And having here a first look, have a look at the demo, have a look at the tool cards. Yeah, I have to show you the tool cards. They are already predefined for you. So my goodness, it's such a nice system. You don't have to pay for a commercial system. Just go with those. This is really latest one. You can enjoy it. I did enjoy it. And hey, if you subscribe, maybe I show you then an integration of this system in one of my next videos.